Alright, you guys. Sorry, today's probably not gonna be too long of one. I'm just gonna attempt one problem. I'm gonna redo this problem, I guess, so technically two problems, and then I'll attempt the hard. And honestly, who knows how long next hard is gonna take, because I remember this medium took us an hour anyway. So let's go. I'm not really looking. Okay. Let's do this one again. It's pretty fresh in my mind, so it shouldn't take too long. Let's see. So if not pre-order or not in order, turn none, then we'll do root equals a tree node where the value is going to be pre-order at 0, I believe. Yeah, and then the index is going to be in order dot index of root dot val. And I'm doing this on LeetCode because, well, I guess one, it'll give me a submission, which is nice. But two, because it won't TLE, like for some reason LeetCode does. So index is going to be the value of the root. So root dot left equals self dot build tree pre-order in order. Root dot right. Oops. Then here we'll return root. Then pre-order, let's see, for root dot right, if you're at 3, pre-order is going to be from, it's going to be up to, well, the answer is it's going to be up to index, right? So index is 1 in order. So index is 1. You want to give it, oh wait. Index is 1. X plus 1. So the same here. In order, you want to give it, oh wait, this is for right. Oh, I'm being stupid. It's 20, so it's 1 on. Let's see, in order, 1 on 1527. Okay, that's good. So pre-order for the left is going to be just 9, so 1 to IDX plus 1, and then in order is going to be just 9, so up until IDX. Let's try that. Great, it looks like it works. Let's submit. Awesome. Okay, well, I guess I could implement the hash map way, which is a bit more tricky. Yeah. Okay. Alright, let's move on to the hard. Binary tree maximum pass sum. Let's see whose question. Facebook. Given the root of a non-empty binary tree, return the maximum pass sum of any non-empty path with a sequence. Okay. I don't know, let's see the solution. And square. Alright, let's see what LeetCode has to say. And I'll mute up.
Hey everyone,
So it
welcome
doesn't-
back and let's
so it
write
doesn't-
some more LeetCode today.
So it doesn't echo.
So
So
today let's solve binary tree maximum path sum. And yes, this is another problem from the blind 75 LeetCode list. So this is a list of 75 common LeetCode questions, and today we're going to be solving this tree question, binary tree maximum path sum. The link to this spreadsheet will be in the description if you do want to take a look. And I think I've almost done all of the problems that I wanted to do from this list, nearly all of them so far. So a path is defined in a binary tree as being a sequence of nodes where each pair of adjacent nodes in the sequence has a edge connecting them, and a node can only appear in the sequence at most once, and the path sum of that path is defined as being the sum of all the nodes' values in that path. So for example, in this example we're given a tree and a could, because how here we can split in two directions, right? We can include a path from here, from the left side, and then we can also go here, right? And if we get to this portion, right, we already had a split up above, so we can't split twice, right? Because then it's no longer a path. So we can only choose one of these nodes. We would obviously choose the bigger one, that's a 5. Right, so take a look. What would the sum be if we ended up splitting from here? This is obviously the max we could create. What is the total? It's 1 plus 2 plus 3 plus 5, which is going to be 11. Now, we're going to try it multiple ways, right? It's possible maybe there could be a split over here. Of course, this doesn't have any children, so the most we could get doing that would just be a 2. But what about over here? What if we ended up splitting from here? So we took the left and the right from here. We'd get a 4 and we'd get a 5. Now, if we did do that, notice how this is going to be the topmost node. So whenever we split from a node, we can't really get any of its parents or anything like that. So in this case, what is the sum of this path? Well, it's going to be 4 plus 3 plus 5, which is going to give us 12. 12 is greater than the 11 that we had previously, so this is going to be the max path sum. So you can tell that a brute force approach would be for every single node, consider it being the topmost node, and then from the left subtree basically find what's the maximum path we could create in the left subtree if we never split. So we can't include both left and right, and then do the same for the right side, right? And if we sort of do it recursively, we can eliminate repeated work. So suppose we're given that same tree. We're going to start at the root like normal, right? So from here we want to know what's the max path sum we could do from here if we split from this position, right, going left and right. Now, why start at the root when we could solve the subproblem first and possibly use that subproblem in the result at the root position? So we're going to leverage that idea, a depth first search idea, just like usual with tree problems. And using that, we're going to end up getting a linear time solution, and it's just going to depend on the return value of our recursive function. So we're going to start at the root. And now we're going to go left, right? We want to know what's the maximum path we can get from the left subtree if we never end up splitting. So in this case, it's pretty simple because it doesn't have a left child or a right child, right? So we don't even end up having to split, and we get a sum of 2 from this spot, right? And even if we were splitting from here, we would get a total of 2 so far. So what we'll say is, so far the max path we've gotten so far is 2, right? Now, we still want to know what's the max we can get from this position, so what we're going to do is now go to the right tree. So recursively, now we're going to ask the question down here, what's the max path sum we can get if we ran it through this position and we ended up splitting left and right? And by the way, our result so far is going to be 2. That's the maximum path so far that we've gotten. So from here, we're gonna, since we're trying to again find what's the max we can get splitting from here, we're gonna go recursive and we're gonna do that for the left subtree and the right subtree. So we're getting that same base case here, right? With this left subtree, if we tried to split from here, the max path we'd get is 4 because it doesn't even have any children, right? So let's keep track of that. The max path we could get from here is 4. Now, if we didn't split here, we'd also get that same value of 4. And that's what I'm marking here. Next to each node, I'm marking what's the max we could have gotten if we did not split. I know it's a little confusing, and it'll make more sense once I actually finish the rest of this example. And so from over here, now we do have what's the max we'd get from the left path without splitting. It's 4, but now we just want to do that for the right side. Once again, it's that same base case, right? So what's the max we could get running through here if we never split? It would be 5. It doesn't have any children, so we couldn't split even if we wanted to. So now we're at this node once again. We have computed the left and right subproblems. Now from this node, we're going to be computing 2 different values. By the way, our result right now would actually be 5 because that's what we've gotten so far. So from this position, I'm computing 2 values. I want to know what's the maximum sum we could get with a path running from here if we are allowed to split. So we are allowed to go right and we are allowed to go left. So what would the total of that be? Well, of course, we would just take, okay, what's the max we could get from the left subtree without splitting, right? Because we can't split again. If we already split up here, we don't want to split again here. So what's the max we could get from here if we never split? Well, it would be 4, right? And once again, what's the max we'd get from here if we never split? It would be 5. So up here, I'm going to take 3 plus 4 plus 5 and say this is the max path running through here if we are allowed to split. Now, this isn't the value that I'm going to return to the parent. The reason I computed this value is so I can potentially update the result, right? And we are going to update the result because this is 12. So far, our result is 5. So we can say that our new result now is going to be 12. Now, what's the value I want to return up to my parent? Remember, what this guy wanted to compute was what's the max it could have if it was allowed to split to the left and it was allowed to split to the right. So from here on, we don't want to split twice. So the question I have for this node when we're returning up to our parent is what's the max I could get running through here if we are not allowed to split? So how am I going to get that? Well, I can take this 3 and add it, but then I have to look at my left subtree and my right subtree and take the max of both of these, right? I have to take the max of them. I can't choose both, so I have to choose one of them. I'm going to take the maximum, which is going to be 5. So I'm going to say 3 plus 8. That's going to be the value that we return. So notice how for each node I'm marking what's the return value from that node going to be. So it's going to be 8 in this case. So then when I return back up to the root, I'm going to say, okay, from here, what's the max path we could get? Well, I'm going to take the node itself, 1, take the left, which is 2, and take the right, which is this path, right? Notice how we don't split. It's going to be an 8, which is going to give us 11. Now that's not bigger than our result, right? So we actually don't update the result in this case. And of course, this is the root node, so it's not going to end up returning to its parent. But what if it did have a parent? What would it return? Well, we would take 1 and then add it to the max of the left or the right. Of course, the right is an 8. This is the path. So we'd say 1 plus 8 is going to be 9. 9 is what we would return to our parent. That's the max path we can get from here without splitting. What would that path look like? Well, of course, it would just be this, right? Notice how this is a path. It never splits. So that is the main idea for this problem. There's one last quick thing I want to go over. So the return value, of course, is going to be for every node, what's the max path without splitting, and we are going to still calculate what's the max path with splitting and use that to actually update our result. We're going to keep this as a global variable because it just makes the code easier, but it is possible to solve this problem without using this global variable. And by the way, if you've been noticing, we're only going to be looking at each node once, so that's going to be a time complexity of big O of n. The memory complexity, of course, is going to be the height of the tree, which is usually log n if it's a balanced tree. But one last case, remember this tree could have negative numbers. So for example, let's say this was a -4 and this was a -5. So then from this left subtree, we would return a -4, and from this we would return a -5. So then, when we're actually computing, okay, what's the max path that could run through here? And let's say we're doing it for the one that we can't split, right? Where we don't split. So we either choose the left or the right. And as I mentioned, how we're doing it is we're just taking the max of the two, right? So in this case, we would take the max of -4 and the max of -5, right? And of course, we'd say the max is -4. So then when we're up here, what we would end up computing is 3 plus -4, which is going to give us -1, right? -1. So what we would say is, okay, the max we could get here without splitting is going to be -1. But that's not actually the case, right? Because to get the maximum path sum from here where we're not allowed to split, it doesn't necessarily mean we have to include the children, right? They're optional. We could actually choose to not include either of these, and that's what we would want to do because they're both negative anyway. Why would we want to include some negative numbers? So when we're actually taking the max of the two, we're actually going to take the max of 3 values. We're going to take the max of the left, right, and potentially 0, because if we just add 0 to it, this will stay the same. So those are the key ideas I wanted to go over. I think that is enough for us to dive into the code to solve this optimally. So like I said, we're going to have a global variable for the result, and initially we're just going to set that to the whatever value happens to be at the root. So the reason I'm making it a list is because that'll make it so that we can modify it within the recursive function a little bit easier. So we're going to have a recursive DFS. We're going to pass in whatever root node we're traversing, and that's really all we have to pass in. So now the base case is that if we don't have a root, like if the node is null, in that case, what we're going to return is just 0. That means we're not going to be adding anything. And so we're going to be returning, I just added a comment, we're going to return from this function the max path sum without splitting. So we want to get the max path sum. So of course we have to do this recursively. So let's get the left max, and we can do that recursively. Just pass in root.left. If it's null, of course, that's just going to return 0. We're also going to get the right max, passing in root.right. So the first thing I'm going to do is compute the max path sum with a split from this root node. So basically what I'm going to do is I'm going to take the root.value and add it with the left max and the right max, right? Because we are splitting from this root node. Now, of course, these left and right maxes could be negative. So what I'm actually going to do before that is update them. So we're going to set left max equal to the max of itself and 0. And do the exact same thing with the right max. So it's going to be set to the max of itself plus 0. So here we're going to be computing the max path running through here. So we're going to take the root value, the left max, and the right max, add them together. Now this could potentially be our new result. So let's see if it actually is. So result at position 0 is going to be set to the max of itself or this value that we just computed. So this is the part where we're actually computing what could actually be the updated result. Now, what the return value, remember, of this function is not going to be the same as this. The return value is going to be what we compute without splitting. So the return value is going to be return root.val plus whatever the max of the left max and
all right, I think I understand it. So result equals, I'll just put it at the val def dfs takes in root if I return, is return none here?
and
return 0. Return 0.
and right max is right.
Left max equals the left, right max equals root right. Left max is the max between left max and 0. The right max is the max between the right max and 0. Equals root val plus left max plus right max. Result equals a max between the result and curve. Return root val plus max between left max and right max. And here we'll we'll call DFS in the root, and then return result. After the result, beautiful. So if instead of this it is self.result, and then instead of non-local result, I do result or self.turn self. Okay. That's a hard. Should I submit this on it only took me 23 minutes. Yeah. Construct binary tree. And that makes some sense though. Binary tree max pass sum. Oh, today's technically the 24th, but it's really the 23rd. Here, let's solve that one on LeetCode. Binary tree. Maximum pass sum. Okay. Self equals takes in the root. If there's not a root, return 0. Left max equals DFS root of zero, curve equals root plus left max plus right max. Self equals a max plus self curve, and then return root max between left max and right max. Let's do a first nodes and K code. Headers and nodes and okay, top. Alright, I think I'm gonna call it a day. Maybe I should do LRU cash again tomorrow, maybe? I don't know. I start classes tomorrow, so I might be a little more occupied than usual, but hopefully I can, actually I don't know if I will be able to, but I'll try my best to, and yeah, we'll see where it goes from there. I'm trying to give myself free time, so we'll see how it works. Alright, but I will see you guys tomorrow, or as soon as possible, I guess.